All right, let's get some more practice here. With this here. For each below, write the formula or name. Dinitrogen pentasulfide. And so we need the formula. Dinitrogen, di is 2 nitrogens, so it's N2. And yeah, which would be S5, N2S5. Again, the N2 is just indicates 2 nitrogens. It doesn't mean that there's diatomic nitrogen gas in this. Dinitrogen pentoxide. It's penta with an A, but they dropped the A to make it smoother. So pentoxide. Dinitrogen pentoxide would be N2O5. Okay, I409 is called, 4 is what? So you should have it, it should be mono-di. Eventually you get mono-di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. That's for the prefixes for numbers. For the numbers of carbon, it goes meth, M-E-T-H, eth, E-T-H, prop, P-R-O-P, bute, pent, hex, hep, oct, non, and dec. You know. So it's similar. So this tetraiodide or tetraiodine? Tetraiodine. It's tetraiodine because the first element does not get the I ending. Only the second. It'd be tetraiodine or iodine. What's 9 again? Nona. Nona oxide or nonaxide or no noxide. Nonoxide. Okay, the last one. Should we call that monophosphorus or phosphorus? Okay, for the first element, remember CO2. Do we call that monocarbon dioxide or just carbon dioxide? And so for the first one, we don't use the mono. For the second one, we would use the mono. And so this one would just be phosphorus, not monophosphorus. And it would be phosphorus. 5 is, yeah, pentafluorine or fluoride. Fluoride, yeah. And so here we have N2S5, N2O5, tetraiodine, nonoxide, phosphorus, pentafluoride. All right, those are what we call the molecular compounds. Now, molecular compounds are typically made up of non-metals, but if a compound is made up of non-metals, is it automatically a molecular compound? No, it might be a what? It might not form discrete molecules, it might just continue. It might be a lattice type structure. How do we know? You either know it or you don't, and so it's kind of hard to guess at it, and so we don't know necessarily. But whether it's a lattice or not, like for example, SiO2, is that molecular or lattice? That's a lattice. I mean, if you ever look at quartz, actually, it can't be visualized. We can take a look at SiO2 crystal structure. SiO2 forms a lattice structure. You know, there's no really distinct end to it. It just keeps going. That's it. But I wouldn't have known that unless somebody told me. That this is quartz and quartz forms an extended lattice. You can tell there are quite significant differences in the properties. Something that forms a lattice like quartz behaves a lot differently than something that forms a molecule like CO2. Now, how similar are CO2 and quartz? Well, CO2 is a gas, quartz is a solid. Here you can see it. The silicons are coated black here. Silicons are coated red here. Silicon's gray here. Silicon's blue here. And then the oxygen and other stuff. CO2 has a high melting point or a low melting point? Well, CO2, CO2 doesn't really melt. CO2 does something called sublime. So if you have a drop of a block of CO2 solid, call it dry ice, and it'll vaporize into a gaseous phase. Does quartz sublime like CO2 sublimes? In fact, if you try to melt quartz, you're going to have a really rough time at it. It's really hard to melt this stuff. So there's certain things that will clue us in that the structures are totally different. Molecules typically are soft. They typically have very low boiling points. But if you don't know, and we just have a formula, I don't know, is that molecular or lattice? It doesn't matter. We can name it as a molecular compound, even though it's not. This would be named silicon dioxide. Okay, but silicon is what we call metalloid, and so metalloids are at the border between non-metals and metals. And so what happens when we have metals and non-metals present, rather than all non-metals? Then we have something called an ionic compound. Ionic compound, the naming system is different. So here, would we call this monosodium monochloride? No. Oh, all right. We don't call it that. Maybe we'll call this sodium monochloride. Would we call this sodium monochloride? No, we don't. We don't use the prefixes. So for ionic compounds again are typically metals and non-metals, and usually the non-metals come first. We'll just say non-metals and metals. And that's what they typically are. Not always, but typically. And so, no prefixes here. The reason there are no prefixes is because we can figure out the ratio. So for example, here, MgCl2, we would not call this magnesium dichloride. Magnesium dichloride, it's not necessary to call that magnesium dichloride. Because this. In ionic compounds, we have ions. Ions are charged atoms, and so magnesium is actually Mg2+. And so we don't call it dichloride because is this Cl2 chlorine gas, the green gas? No. What this 2 represents is that we have 2 of these Cl's. And these Cl's actually have a negative charge. And so if we try to put 3 Cl's, there's a problem. If we try to put 3 Cl's, the charges don't balance. This has to be electrically neutral. Otherwise, when there's a charge imbalance like this, it's not stable. So here we have a 2+ charge and a 3-. And so 2+ and 3- gives us a -1 charge. That gives us a net charge. Versus if we only had 1 Cl, then the charges aren't balanced, so we need 2 Cl's. So we could figure out that we have 2 Cl's, just like we could figure out that we have 1 Cl here because the charge on sodium is +1. And so this is just called magnesium chloride. Magnesium chloride. And so there's a bit of memorization that you have to do. One, how did I know the charges on those? Well, the charges, there's a certain pattern for the charges, and that's based on the periodic table. When these form ions, we can see what the charge on the ion is based on its position in the periodic table. All right, so let's look at first the okay, so the name of this is the name of the cation. You know what a cation is? A cation is a positively charged ion. And this is the name of the anion. And all we do in naming this is we separate it with a space. And so we write the name of the cation followed by the name of the anion. It's anion. Anion, the an refers to negative charge, the cat refers to positive charge. So there's a negative charge here, or negative ion. All right, so when we look at the periodic table, we can determine the charges on many of the ions just based on its position in the periodic table. So what we'll look at first are monatomic or monoatomic cations. Monatomic cations, let's take a look at lithium. For example, lithium has 3 protons, and it depends if we're talking about lithium-6. If we're talking about lithium-6, how many neutrons does lithium-6 have? Six. Lithium-6 has how many neutrons? So if I'm dealing with lithium-6, it would have 3 neutrons. Lithium-7 would have how many? 4 neutrons. And so it depends if I'm dealing with lithium-6 and lithium-7. Lithium-6 and lithium-7 are the 2 isotopes of lithium, current nature. Do you know which one's more abundant? Is it lithium-6 or lithium-7 that's more abundant?
Lithium-6.
Lithium-6 is more abundant? You know what the black number is there?
Yeah.
Black number is the average. In fact, I would say non-lithium-6 is lithium-7. And I'd say it's greater than 90%. In fact, I'd say it's more like 94% lithium-7, about 6% lithium-6. Does that make sense? Looking at the number. All right. What happens is this: lithium, when it forms an ion, something comes along and takes electrons. So it actually has 3 electrons to begin with, and something can come along, take an electron, or an electron can be broken off this, and so we end up with a free electron. But we end up with a lithium ion. The lithium ion is going to have a positive charge. We still have 3 protons. The number of neutrons makes no difference in the charge. But now we have 2 electrons, so there's an imbalance of protons and electrons that leads to a positive charge here. So that's it. It turns out that whole family, which is called the alpha earth metals, will all form positive cations. So what is the name of lithium plus? We just call it lithium. But if I'm talking about lithium, am I talking about lithium metal, that heavily corroded metal, or am I talking about lithium ion here? Well, it's ambiguous. And so normally what I have to do is I have to add something to this. I have to add like the word ion or the word cation to indicate that I'm not talking about lithium metal. And the same thing goes with sodium. You know, the name of this is sodium, but is it the metal or is it the ion? In this case, it's the ion, sodium ion. Potassium, rubidium, cesium. All these form +1 ions. And so that's why we call the monatomic cations with fixed charge. Fixed charge is they always end up being the same charge. Lithium always ends up +1, sodium, potassium, rubidium, cesium all follow +1. The other fixed charge would be like magnesium. Magnesium's always +2, but rather than calling it +2, we call it 2+. Calcium, strontium, same. Barium is the same. And so all those form +2 or 2+ cations. the fixed charge, when we're looking at the fixed charge members are what we call main group. Main group consists of two blocks in the periodic table. It consists of this block here, of these two columns, and it consists of this block here, but not all of this block, part of this block. And so the way we do that is something like this. We go from there, we'll catch aluminum. Do you know what the charge on aluminum is? It's 3+, and this is aluminum ion. And so when we look at the periodic table, the species with the fixed charge so far are like this. This has a +1 charge here. This is a +2 charge here. And then we have a +3 charge here. The species here, okay, this block in the center is called the transition metal block, or transition metals. And then the bottom part of the main group would be these two big blocks here. And so part of the main group is cut in here. And what we call these are the variable charge. Ions here. These were for the cations, and these are for the positively charged species. And so for variable charge, we name these differently. Variable charge monatomic. So an example of variable charge monatomic would be iron 2+ and iron 3+. And so we can't call these both iron ions. So the first one we call iron, Roman numeral 2. The second we call iron, Roman numeral 3. These are the ions here. Now iron 2 has an old name. The old name is based on the Latin ferrium. We changed the ending to ferrous. So this would be the ferrous ion, and this one would be called the ferric ion. So these are the old names for these. And so when we're in this group here, this block, these are all variable charge. Lead. You know, if I'm talking to the lead ion, I could be talking about lead 2+ or lead 4+. Lead 2+ is just called lead 2, Roman numeral. Lead 4+ is lead 4, the Roman numeral here. Now, ALS does not refer to a 2+ charge. ALS refers to the lower charge cation. IG refers to the higher charge ion. And so in this case, the lower charge ion is saying it's a 2+. So this is called, well, the Latin for is plumbum, so we're going to call this plumbus. Now the IG, well, this IG referred to 3, but +4 is a higher charge in the lead, so this is called plumbic ion. And so we have a variable charge. Now the variable charge is tricky because within the variable charge lies a small island of fixed charge species. This small island of fixed charge species begins here, and it forms a little elbow of 3 elements here. These are fixed charge species in a sea of variable charge species. So these are fixed charge. And so what are they? Well, what forms at that little elbow is zinc. Zinc is always 2+. Cadmium. Cadmium is always 2+, and silver is always +1. And so here, when I'm talking about the zinc ion, there's no confusion. There's only one zinc ion, and that zinc ion is 2+. So we don't need the Roman numeral for zinc. It's always 2+. Silver ion is always +1, and cadmium is always +2. And so there are ways you can remember this. For example, this, if you look at the heading here, this is called group 1A. And this one's called 2A. And so we have 1A, which has a charge of +1, and 2A, which has a charge of +2. When we look at this one, what group is silver in? Well, we have different numbering systems for the group. So if we look at silver, silver's in group 11, aka 1B, or Roman numeral 1B. And so there's a little clue here, and that is 1A's over here, 1B's over here. What charge is silver? 1B. Silver is +1. If you look at zinc, okay, over here, magnesium is in group 2A, but when we go to group 2B, we have zinc. Zinc is +2. And so there's no coincidence here. It was purposely done this way because these are similar to those in the sense that it's +1 and +2. I'm sorry, remembering. All right, so those are the variable charge cations, monatomic, and then we look at the polyatomic cations next. The polyatomic cations are going to have more than one atom. Polyatomic cations, there aren't that many that we have to worry about. One of them is Hg2 2+. Hg2 2+ is diatomic mercury with a charge. Diatomic mercury with a charge is going to have a different name than mercury. We call this one based on the charge of each mercury. If you have two mercuries with a total charge of 2+, that means each mercury is +1. And so this is mercury 1 or mercurous. However, mercury 2 is a monatomic. So this is a monatomic. And this is mercury 2, in which this mercury has a 2+ charge. Up here, each mercury has a 1+ charge. So this is monatomic here. Mercury 1 is polyatomic. The other polyatomic ion that we worry about is NH4+. NH4+ is called ammonium ion. These are all, I think, all of them. All right, the next thing we're going to look at are the anions. The anions are the negatively charged species. And so in the name of an ionic compound, first we name the cation, and so we pick one of these names here, and then we go on to the anion. For the anions, we have some anions that are pretty simple. We have the monatomic anions that end in "ide." Monatomic anions that end in "ide" are things like this. So fluoride, chloride, bromide, iodide. All these are going to have a -1 charge, and what we do is we change the ending to "ide." Oxygen has a 2- charge. We call this oxide. Nitrogen has a 3- charge. We call this nitride. So we just change the ending. The charge we can figure out because all these, the halogens, have a -1. And so chloride would have an extra electron. It would have 18 electrons rather than 17, which gives it a negative charge. So it'd have the same number of electrons as argon. What about sulfide? Well, what happens here is fluorine's -1, which gives it 10 electrons. Oxygen's -2, which gives it 10 electrons. Nitrogen's -3, which gives it 10 electrons. So they all want to get to 10 electrons. Chlorine's 17 electrons, it wants 1. Sulfur's 16 electrons, it wants 2. So we call it sulfide, S2 minus. Phosphorus is 15 electrons, it wants 3, so that's phosphide. So we can carry this down. So oxide is that, S2 minus would be sulfide. Below nitrogen is P3 minus is phosphide. And so these are the monatomic that end in IDE. In fact, all the monatomics end in IDE. Now we're going to have polyatomics. Polyatomics are more than one atom. We're going to have some polyatomics that end in IDE. The polyatomics that end in IDE, you just memorize those. And so what are the polyatomics that end in IDE? There's one that consists of an oxygen and a hydrogen combined together, and this whole thing carries a net negative charge. This one's called hydroxide. Then we have another with a C and an N. C and N together with a negative charge is called cyanide. Can you think of any others? Peroxide. Another one. This is a polyatomic that is two oxygens. Each oxygen has a -1 charge. And if we have two of those, -1, we have net -2 charge. This is called the peroxide ion.
Iodide?
Iodide is iodine. That would be a monatomic. All monatomics end with I. In fact, monatomics, you just change the element name to I. So this is iodide here. Whereas, did we just change the element here? You know, if we have cyanide, it could be we have the element cyanium. Is there such an element as cyanium? No. If we have some name like fluoride, there's an element called fluorine. We just change the ending to "ide," so that would be up there. Now, there are some others. There are others, but the others you don't need to memorize. So, for example, do you know O2 minus? O2 minus is called superoxide. Superoxide. But we don't need to know that. I think these are it. These are the only ones that you'll encounter here. And those are the polyatomics that end in ide. Then we're going to go to the polyatomics that end in ate. And so if you have an ending ide, you got to think monatomic or polyatomic. If it's monatomic, it's just the element. If it's polyatomic, then it's one of these here. Okay, if you have an anion that ends in, this would be polyatomic, that ends in 8. Then we have two categories for the 8s. We have the periodic table. Eights. The periodic table 8s look like this. If we look at the periodic table, let's go ahead and draw part of the periodic table up here, starting with boron. If we go to boron, and then what comes after boron? Carbon, after carbon, nitrogen, oxygen, fluorine, and then go down. Chlorine, bromine, iodine. And then we look at the ions. Borate, this one would be called carbonate. This one would be called nitrate. Oxate, there's no such thing as, but fluorate there is. Fluorate. Chlorate there is. Bromate there is. And iodate there is. Okay, then we look up the formulas for these things. When we look at the formulas for these, that is the composition of the charge, the formula for borate is BO3 with a 3 minus charge. It's a 3-3. What group is boron in? Look at the heading. It's in group 13. aka 3A, aka 3A, Roman numeral versus whatever numeral. And so this is in group 3, and so it's easy to remember 333, right? And so we memorize borate. But if we memorize borate, then we got to memorize the others, but we really don't have to memorize the others because you'll see a pattern. Take a look at what carbonate is. Carbonate is CO3, 2 minus, nitrate is NO3 minus, fluorate is FO3 minus, chlorate is ClO3 minus, bromate is BrO3 minus, and iodate is IO3 minus. Do you see a pattern? The pattern is all of these have how many oxygens? 3 oxygens, and then look what happens to the charge. It goes 3, 2, 1, 1, 1, 1, 1. And so we're okay. So as long as we can remember borate, then we can figure out the rest. Well, there's one more pattern in here that I'd like you to memorize, and that deals with below carbon is silicon. And so we have silicon, below nitrogen is phosphorus, below oxygen is sulfur. Below phosphorus is arsenic, below sulfur is selenium. Below silicon, do you know what is below silicon element? Germanium, below silicon. All right, now what we do is we memorize silicon, that is silicate. Phosphorus would form phosphate. Sulfur would form sulfate. Germanium would form germate. Arsenic would form arsenate. Selenium would form selenate. All right, what's the formula for silicate? The formula for silicate, if you're a geologist, you know this, perhaps after mineralogy, but it's be SiO4 4 minus. What group is silicon in? Group 14 or 4A. And so we memorize this, silicate 444, right? Do you know the formula for phosphate? The formula for phosphate is PO4 3 minus. The formula for sulfate is SO4 2 minus. Do you see a pattern? Yeah, there's a pattern there. That pattern might let us predict. What do you think selenate is? Or actually, let's go here. Let's go here. Nitrate's this, phosphate's this. What do you think arsenate is? ASO5? 5 minus? ASO6? 5 minus? What do you think? Well, it turns out that arsenate is ASO4 3 minus. It's the same. Well, if arsenate's like that, what do you think selenate is? SeO4 2 minus. SeO4 2 minus is correct. Germinate? Germinate, not germinate. Germinate. Germinate? GeO4 4 minus. That would be correct. And so this is the pattern here. And so we could go down. Below arsenic is antimony. So antimonate would be SbO4 3 minus. And so that would be the pattern. We have the inside, the blue, so I'll just write etc. here, blue. And then we have the outside, which is the black here. Okay, those are the 8s that come off the periodic table, so we need to memorize 2 of those 8s, to get the whole table. And then we have some more 8s that we just have to memorize by a straight memorization. And so we have B, the other eights. The other eights, just straight memorization. And so what are the other eights? The other eights would be things like acetate. Acetate, well, we just have to memorize it. Acetate is C2O. Actually, that's not it. What is acetate? C2H3, C2H3O2 minus, or CH3COO minus in that structural form. That's acetate. What else do we have to memorize? Oxalate. Oxalate is C2O4, 2 minus. We have to memorize chromate. Chromate is CrO4, 2 minus. We have to memorize dichromate, which is Cr2O. We'd like to say 8, but it turns out it's 7. Cr2O7, 2 minus. Charge is the same. It's how the two chromates link together to form a dichromate. Di is just 2 chromates. So we have to drop an oxygen or lose an oxygen. We maintain the same charge based on how they link. So we got chromate, dichromate. What else? Sulfate is off the periodic table. SO4, 2 minus. We have something similar to sulfate, but before I get to that, let's talk about permanganate. Permanganate is MnO4 minus 1. A little tricky to remember, permanganate. We have something similar to sulfate. It's called thiosulfate. Thiosulfate, thio refers to sulfur. And so whenever you see thio, replace an oxygen with a sulfur. Replace O with S. The charge doesn't change, and so same charge. And so we know sulfate, that's one of those ones off the periodic table, it's SO4, 2 minus. Let's remove one oxygen. If we remove one oxygen, how many oxygens do we have left over? 3. So we have 3 oxygens. And then add a sulfur. If we remove an oxygen and add a sulfur, how many sulfurs do we have? 2. And then we have the same charge, it's 2 minus. So this is called thiosulfate ion. Your book is going to ask you to memorize more. Your book is going to ask you to memorize cyanate and thiocyanate. Cyanate and thiocyanate, you don't have to memorize those. We don't do much with those particular ions, so it's not really necessary. Okay, those are the 8s. Did I miss any? All right, after the 8s, we have the ites. The ites have 1 less oxygen, same charge. So, sulfate is SO4, 2 minus. What is SO3, 2 minus? So sulfate is SO4. SO3 would be sulfite. It has the same charge, 1 less oxygen. So we don't really have to memorize sulfite as long as we know what sulfate is, right? NO3 minus is nitrate. NO2 minus is nitrite. So those are the ites. And then we have those are the endings. We have the prefixes per. Per is 1 more oxygen, same charge. So an example of that would be ClO3 minus is called chlorate. And therefore ClO4 minus has 1 more oxygen, same charge. We call this perchlorate. would not call something perchlorite, because perchlorite would be the same as chlorate. Perchlorite is one more oxygen than chlorite, but we already have chlorate, which is one more oxygen than chlorite. And then we have the hypo. Hypo is one less oxygen. So, numbering scheme's not messed up, but hypo means one fewer, one less oxygen, same charge. And so the way it would go like this, here we have chlorate, 8. And then one less oxygen would be ClO2 minus, this would be ite. And then one less oxygen than that would be an ite. But rather than calling it an ite, we're going to call it a per-ite. So ClO minus is per-ite. And then if we have one more oxygen than this, we call it hypo. Sorry, hypo is less. Hypo. One more oxygen than this would be per. And so this would be ClO4 minus. All right, I think I've got a time here. So we'll do some practice next time. I would get started on memorizing some of the names of the ions here. Names, charges, and formulas. We'll just meet. It's the first part, we're going to go adjust. This is more, it's multiple choice, more important. Well, what do you think of the practice test? Do you think hard, easy, wasn't bad? Okay, then this is not bad.
Oh, okay. Good to know. That's very good.
Okay, great. Thanks.
Make sure the rules are in one section, and then like another section. So for the textbook, that's chapters 1 through 5.
Part of 5.
Part of 5.
All right.
And then tomorrow is test and lab.
No. Test. Well, lab meaning we're going to finish up some of the calculations from the previous lab.
All right.